Hi everyone. Today we're going to talk about Kruskal's algorithm. This is something that's often used in network engineering and computer science and has a lot of real-world applications. Basically, it's designed to take a weighted connected graph and from it create a minimum weighted spanning tree using a greedy algorithm. Now, what exactly is a weighted graph? Well, it's a graph where the weight or cost is assigned to each edge. So for example, let's turn this graph here into our weighted connected graph. We're going to go ahead and add some edges. And to those edges, we're going to assign costs. And for that, I'm going to go ahead and use integers, but you can use non-integers as well. Okay. When running Kruskal's algorithm, we're going to call this weighted connected graph G, our input. And the graph that is going to be constructed by the algorithm itself is going to be our output, and I'm going to refer to that as T. Keep in mind that Kruskal's algorithm creates a spanning tree, which is a connected acyclic graph on all vertices. So the vertices in G have to be the same as the vertices in T, and you can see that that holds true for the graph that I'm using below. Before we begin Kruskal's algorithm, we have to actually list the edges of G in increasing order of weight. So what do I mean by that? Well, if we look here, the lowest weighted edge is 1, and that is between vertices 1 and 3. And I am going to list the rest of those in increasing order. So the next one could be 1, 2, or 2, 3, as they both have a weight of 3. But the important thing to remember about Kruskal's algorithm is if I do have something or two edges that have the same weight, I can just add them arbitrarily to my list. It doesn't affect the algorithm at all. Okay. So once the list is created, the first actual step in the algorithm is to take the lowest unweighted edge, which you can see is a weight of 1, and we're going to go ahead and add that to T. This provides our initial tree. After this initial edge is chosen, we're going to proceed to work our way through the list by adding the lowest weighted edge that is available to T. So the next weighted edge that's available is 1, 2, which has a weight of 3. However, there are two things we have to keep in mind. One is that we cannot add an edge that will create a cycle in T. And then the second thing is that if we do have two edges of equal weight, as we again do here, I can add them arbitrarily to T as long as they do not create a cycle. So I'm going to go ahead and pick the one that's first on my list, which is 1, 2. That does not create a cycle, so it is allowable. However, the next one on my list, 2, 3, does create a cycle in T. So I am going to discard that one. It will not be added to my final graph. Then I'm going to go ahead and continue with the algorithm, 3, 4. That is allowable. And here we reach a point where I actually, if you count my vertices, I have 4 vertices. And right now I have n-1 edges. Now, if you recall from the definition of a tree has n-1 edges. So at this point, I know that I am done and we have a spanning tree. Now, if you do want to see the proof behind this particular property, you can look at Theorem 2.1.4 in the West textbook, and that will give you more information on properties of trees. Now that we've seen Kruskal's algorithm in action, let's talk about how we know that it actually does construct a minimum weight spanning tree. So in order to prove this, we actually need to show two primary things. The first one is that a spanning tree is actually produced. And the second is that T is going to be of minimum weight. So I mentioned earlier that a spanning tree is an acyclic connected graph on all vertices. So we're going to prove T is a spanning tree by showing that three conditions hold for T. The first of these is that T is a forest. The second is that it is spanning, so it's on all vertices. And the third is that it is connected. So let's go ahead and start with A for now. T is a forest. Well, if we look back to the rules used in our earlier example, we saw that we were adding the lowest weighted edge that did not result in a cycle. If it did create a cycle, we were going to discard the edge and not add it to T. So since the algorithm itself can never select an edge that results in a cycle, the resulting output has to be acyclic. And if you recall from our text, an acyclic graph is the definition of a forest. All right, so that bit is fine. Let's move on to showing that it is spanning. If we know T is a forest, we have to show now that it's on all vertices of G. So let's say that we have a graph T that includes vertices U and W. So VT equals the set of those vertices. And let's say we have an isolated vertex V that is not a part of that graph. Well, since we know from our initial input that G has to be connected, there has to be at least one edge connecting V to U and W. So it could be here or it could be here. And that's in G. So by the rules of the algorithm, the first of these edges has to have already been considered and added to the graph. So I could have already added VU or VW depending on which one was weighted lower. Let's say that the lower weighted one was UV. The second edge has either been considered, or in this case, it's created a cycle and has already been discarded, again, going by the rules of the algorithm. So this shows that T must be spanning. And on all vertices. And then the final thing we have to show is that T is connected. And this is basically the same argument as what I used for the one above. If T is not connected, then it must have at least two connected components because it was connected to NG. So let's say I have two connected components in T. Now again, G was connected, so at least one edge has to lie between these in G. It could be up here, or it could be down here. So either the edge didn't create a cycle and has to be accepted by our algorithm, or it did, in the case of one down here, and was discarded by the algorithm. So either way, T has to be connected by the rules of the algorithm, and therefore it must be a spanning tree. And this is just based on the definition that a connected acyclic graph is, by definition, a tree. So now that we've determined that Kruskal's algorithm does actually produce a spanning tree T, let's go ahead and discuss how we can show that T is of minimum weight. So in order to do this, we're going to create another spanning tree, and we're going to call that T prime, that is hypothetically of minimum weight. And let's go ahead and fill out our edges for both of these. So T, which is what we're assuming was created by Kruskal's algorithm, has these edges. And we'll call this one F and this one E. And then the one that is our hypothetical minimum weight tree is this. We'll call that one E prime, and we have F prime as well in this one. Okay, if T was in fact the same as T prime, we would be finished with the proof because we would know at that point that T is a minimum spanning tree. But let's assume, as you can see, that T is actually not equal to T prime. So this means that there has to be at least one edge in T prime that is not in T. And if you look at our graphs, we can see that the edges E prime and F prime are not in T. And then you can also see that the edges E and F are not in T prime. So because T prime is a spanning tree, we know that moving one edge from T, and let's go ahead and say F, to T prime, like this, will result in a cycle. Otherwise, T wouldn't be a tree, and T prime wouldn't be a tree. So we can see this here, that would create a cycle. Because, however, the algorithm chose originally F instead of F prime, we actually know that the weight of F has to be less than or equal to the weight of F prime. So we can actually permanently move F to T prime, giving us T prime plus F minus F prime. And we do have to remove F prime because otherwise, again, we're going to end up with a cycle, and that is prohibited by our algorithm. We also know at this point that in addition to the weight of F being less than or equal to the weight of F prime, we know that our new tree, WT, has to be less than or equal to WT prime. All right, the resulting graph is also, you can tell, closer in shape than what we initially started with. So we can repeat this process again, this time with E. We can take E and move it to T prime. However, in order to do that, we're going to have to remove E prime, otherwise we have a cycle. So there we go. And again, we know that the weight of E has to be less than or equal to the weight of E prime, because otherwise Kruskal's algorithm wouldn't have chosen that one to begin with. We can proceed to do this for every edge that's not the same. So we also have this one up here we could repeat the process on and move to T prime until we end up with a graph that is the same as T. So in that case, T prime would be equal to T. And because we've already said that T prime is our hypothetical min weight graph, we know that T in this case would also be a minimum weight spanning tree. And that does conclude our proof. So the last thing I want to talk about today is a real-world example of this algorithm in action. So I mentioned earlier that it was used a lot in network engineering and computer science, and it was actually initially studied as a way to reduce the cost of wiring in electrical networks. So I want you to look here at my input, which is going to act as our network. These are the costs of wiring between the two nodes. So for example, if I want to run a wire between node 1 and node 2, it's going to cost me $2. If I want to run a wire between nodes 1 and 4, it is actually I'm going to get money back. Perhaps that is wire that we are just not interested in selling and want to get rid of, etc., etc. So if you look at it this way, the way it's wired currently, we actually have a cost of $18. But using Kruskal's algorithm, we are going to create a minimum spanning tree that is going to give us a minimized cost. So following the exact steps that we did at the beginning of the video, we're going to go ahead and list all of our vertices in order of weight. So 5, 6 is actually the lowest weight at -$2, and continue on from there. So 1, 4 is -1, 2, 6 is $1, 1, 2 is also $1. Excuse me, 1, 2 is $2. 4, 5 is $2, and 1, 2 we've already done. 2, 3, $3. 2, 4 is $4. Obviously, if we were doing this on larger networks, we would have a computer do this for us, which is why it is an algorithm. It works fine by hand for smaller networks, but I mean, you can clearly see that the more nodes we add, the harder this gets, or at least more time consuming. Okay, and 3, 6 is our most expensive thing at $5. All right, so again, going back to the beginning of the video, in order to do this, we are going to choose our lowest cost edge, or wire in this case, and we will add it to our output graph. So 5 to 6. And 1 to 4 is fine. It does not create a cycle, so I will add that. 2 to 6 is also fine. It does not create a cycle. I can choose between 1, 2, and 4, 5. I'm going to do it in the order that I wrote them. So 1, 2 does not create a cycle and is okay. 4, 5, however, is going to create a cycle, so I am going to discard that. 2, 3 does not create a cycle. And once I get to 2, 3, you can see that we have n equals 6. And now the edges in our output graph equal n minus 1. 1, 2, 3, 4, 5. So I know at this point that I have a spanning tree. And let's go ahead and compute our final cost on this. We can stop the algorithm. 5, 6 was -2. This was 1, this was 3, 2, and -1. So we actually end up now with a total cost of $3. And from the proof, we know that this is indeed the minimum weight spanning tree. And that's all there is to it. Kruskal is quite useful and a very easy thing to learn. Thank you very much.